In order to make comparisons between our observations, not only do we need to know what changes have occurred, but how much change. In order to make consistent measurements, we need to use a standard method of measuring. So for example, we have a tape measure here which has two different standards, inches and centimeters. We can use these no matter where we are as long as we have a tape measure which is calibrated to the right scale and know that we'll get the same results as somebody else on the other side of the world. What this also means is that we need to be able to convert between different systems, so that if one person is using inches and the other person is using centimeters, we can compare those observations together. In order to maintain consistency between scientific measurements, scientists have come up with a system of measuring which is standard across the scientific community. This involves kilograms for measuring mass, meters for measuring length, and liters for measuring volume. And together with a few other standard units, we can use these to measure all different types of scientific measurements. It's also important to recognize scale when we're making measurements. For example, when we're measuring drug molecules in a pharmaceutical preparation, we use milligrams. This is 1,000th of a gram. When we are measuring the nutritional content in a candy bar or other foodstuffs, we use grams. And when we are measuring larger materials, such as this bag of cement, we would use kilograms. All of these are based on the same unit. We have kilograms, grams, and milligrams. This prefix, m, is for milligrams. Gram has no prefix, and then kilogram, the prefix is included in the standard measure, kilo meaning 1,000. So depending on what we're measuring, it's important that we use the right scale. The example on the left here shows the relationship between kilograms and milligrams. A kilogram is 1,000,000 times a milligram. What this means is that we can make a measurement in kilograms, but we would have to put all those decimal places in there. If we use milligrams instead, it means that there's much less likelihood of making a mistake in the number of zeros, or it's just an easier number to deal with. It's important to be able to convert between these two units so that we can maintain consistency in our calculations. We can also use exponential notation. For example, we could write this down as 3.42 times 10 to the minus 5 kilograms as opposed to 34.2 milligrams. This again avoids having all those zeros and makes it much easier to see the number of digits that we're really interested in. In making measurements, we not only want to be precise, but also accurate. In common usage, precision and accuracy are used interchangeably, but from a scientific perspective, they have significantly different meanings. A slow watch, for example, no matter how precise, will never be accurate. Precision is a measure of how much detail we give in our measurement. If we give the measurement of the time down to the 100th of a second, this is very precise, but if we set the clock an hour slow, it's never going to be accurate. Accuracy, on the other hand, is a measure of the closeness to the true value. The example I've given here is an arrow hitting a bullseye. The closer you are to that bullseye, the more accurate you are. This exemplifies that idea that accuracy is a measure of how close you are to the actual value or to the target value. When we make a measurement, there will always be some kind of uncertainty associated with making it. For example, if we use a tape measure to measure the width of a room, we can be more certain with our measurement than if we merely paced across the floor. The way that we convey uncertainty in science is using significant figures. On the left we have 3 significant figures from American history. On the right we've got 4 measurements, all of which are given to 3 significant figures. The number of significant figures is the number of important digits, or the number of significant digits, that are needed to interpret that measurement. We count significant figures starting from the first non-zero digit on the left.